Welcome back, everyone, to today's explainer. If you've ever, tinkered around with a microcontroller, wired up a new sensor, or even just prepped for a hardware engineering interview, I can practically guarantee you've crossed paths with the Serial Peripheral Interface. A lot of people just call it SPI or SPI. It's an absolute powerhouse of a protocol that Motorola actually developed way back in the 1980s. So today, we're going to completely demystify it. By the end of this explainer, you're going to know exactly how this protocol ticks, why it's just so incredibly popular, and how you can conquer it in your own hardware projects.
Okay, let's look at our roadmap for today. 1. Why choose SPI? 2. Decoding the 4 wires. 3. Mastering polarity and phase. 4. Connecting multiple slave devices. And finally, 5. Ace your SPI interview. Let's dive right in.
Section 1. Why choose SPI? And really, it all comes down to the need for speed.
So if you're working on an embedded system, you usually hit a fork in the road. You got to choose between I2C and SPI. Now, I2C is a half-duplex protocol. Think of it kind of like a walkie-talkie, right? Only one side can talk at a time. It uses this really elegant built-in addressing scheme, but honestly, it's relatively slow. SPI, on the flip side, is full duplex. That means both the master and the slave can send and receive data at the exact same time, more like a regular telephone call. Now, you do sacrifice that nice built-in addressing, but in return, you get raw, blazing fast speed. We're talking megahertz range here. When you need to push a massive amount of data really quickly, SPI is absolutely your go-to.
And honestly, because of that incredible speed and the simultaneous data flow, SPI is literally everywhere. You're going to find it heavily used in sensors, like gyroscopes, for instance, which need to constantly stream position data. It's in high-refresh LED displays, analog-to-digital converters, DACs, real-time clocks, and yeah, even those wired game controllers we all used growing up. Basically, if a device is considered a less smart peripheral that just needs to talk to a smart microcontroller really fast, it's probably using SPI.
All right, moving on to Section 2, decoding the 4 wires. Let's look at the physical connections. SPI is fundamentally a master-slave protocol. You've got a single master and 1 or more slaves, and they're typically hooked up using 4 distinct wires. First up is the clock. This is entirely generated by the master. And this is actually a huge deal because since the master controls the timing, the slaves don't need their own built-in timing crystals. That saves a ton on hardware costs. Next, we have chip select, or CS. Now, unlike a lot of digital signals, this one is active low. That means the master pulls the voltage down to 0 to wake the slave up, essentially tapping it on the shoulder to say, hey, I'm talking to you. And finally, we have our 2 data lines, MOSI and MISO.
So the crucial point here is understanding exactly what these 2 data lines actually do. Luckily, the names are wonderfully literal. MOSI stands for Master Out, Slave In. It's the wire carrying data bits from your main controller down to the peripheral. Then you have MISO, which is Master In, Slave Out. That's the wire carrying data from the peripheral back up to the controller. Depending on the hardware vendor, you might actually see these labeled a bit differently on datasheets because, as we'll see later, SPI is pretty loosely defined. But functionally, it's simple. 1 wire sends data out and 1 wire brings data back.
Which brings us to a fantastic trick question. You might actually get hit with this in a technical interview to test your practical, real-world understanding of the protocol. We literally just called it a 4-wire protocol, right? But is SPI strictly a 4-wire protocol? The answer is a resounding no. No way. It turns out the MISO line is entirely optional depending on the specific hardware. Let's think about an LED screen for a second. Your microcontroller needs to blast a ton of pixel data over to that display using the MOSI line. But the display, it never really needs to send any data back to the microcontroller. So for output-only devices like that, manufacturers will often just drop the MISO wire entirely to save on manufacturing costs and free up pins. So a 3-wire SPI setup is completely valid and actually super common out in the wild.
Okay, Section 3. Mastering polarity and phase. Because in SPI, timing is everything. So, since the master generates this continuous clock signal to keep everything in sync, the master and the slave actually have to agree on what that clock signal looks like, and this starts with clock polarity, or CPOL for short. This just defines the resting or idle state of the clock wire when there's no data moving at all. If CPOL is 0, the clock idles at a low voltage, meaning it has to pulse high to become active. If CPOL is 1, the clock idles high and drops low to activate. Really, it's just a question of whether the system takes a break at 0 volts or takes a break at a high voltage. Next up is clock phase, or CPHA. Now this dictates exactly when the receiver should actually look at the data line to read a bit. For every single clock pulse, there's a leading edge, that's the first time the voltage changes, and a trailing edge, which is when it changes back. If CPHA is 0, both the master and the slave sample the data on that leading first edge. If CPHA is 1, they wait, and they sample the data on the trailing second edge. And listen, the master and slave absolutely must be configured to the exact same phase. If they aren't, they're just going to read complete gibberish.
Now, if you combine these two parameters, you get 4 possible configurations. We call these SPI modes 0 through 3. As a golden rule, a true best practice for hardware bring-up, always check your peripheral's datasheet first, then configure the master device's control register to match those exact settings before you initiate any clock signals. Even though there are 4 distinct options, mode 0, where the clock idles low and data is sampled on the leading edge, is by far the most common setup you're going to see out there.
But hey, what if you don't have the datasheet? Or what if your communication is just straight up failing and you don't know why? Well, you can actually reverse engineer the required mode using an oscilloscope. It's pretty cool. By looking at the physical waveforms, you just check the clock line in those quiet moments between data transmissions. If it's resting flat at 0 volts, boom, you know CPLES is 0. Then you look at the MOSI line and see whether the data voltage stabilizes perfectly aligned with the first edge of the clock pulse or the second edge. That instantly reveals your clock phase. It's a fantastic troubleshooting step to help you quickly identify clock phase errors and fix your firmware's register settings.
Section 4. Connecting multiple slave devices. Let's scale up the complexity a bit.
So, what if you have more than one peripheral? There are 2 primary network topologies for multi-slave setups. First, we have independent slaves. In this setup, the master, MOSI, MISO, and clock wires are all shared across the board, but every single slave gets its own dedicated chip select wire. So to talk to slave number 2, the master just pulls CS2 low. It's incredibly straightforward to write code for, but it scales terribly. Eventually, your microcontroller is just going to run out of physical pins. The alternative is what's called cooperative slaves, or a daisy chain. Here, all the slaves share just one single chip select wire. Now, while that absolutely saves on physical wiring, it creates much longer data lines. That means you have to be super careful with your wiring routing to reduce noise and signal crosstalk, not to mention having to manage a highly complex data flow in your software.
Let's walk through that daisy chain data flow. First, the master pulls that one shared CS line low to wake everybody up on the line. Then, the master pumps data into the MOSI pin of slave 1. Now, as more clock cycles tick by, slave 1 pushes that data right out of its MISO pin directly into the MOSI pin of slave 2. It acts exactly like a bucket brigade, just passing the bits down the line until the very last slave's MISO connects all the way back to the master to close the loop. It is a really elegant hardware solution, but it demands very, very careful software tracking by the master device.
Finally, Section 5. Ace your SPI interview. Some rapid-fire tips. Now, a super common technical interview question centers around SPI's strict timing rules, or its signal integrity standards. When they ask you this, your answer should be that SPI is famously loosely defined. Unlike a lot of other strict protocols, SPI has no standard data framing. You could send just 1 byte, or you could hold the CS line low and stream 1,000 bytes. There's no mandated bit order either. It's entirely implementation dependent whether you send the least significant bit first or the most significant bit first. Guys, there aren't even standardized voltage levels. It is practically the Wild West of hardware protocols. But that's exactly why it offers such incredible flexibility for hardware vendors to design exactly what they need for a specific task.
So, I want to leave you with this final thought. Since SPI is so loosely defined, literally stripping away rigid rules in favor of sheer, unadulterated speed, what creative configurations will you invent for your next custom hardware project? Are you going to run a massive daisy chain to save pins? Will you build a blazing fast 3-wire display setup? The implementation is entirely in your hands. Thank you so much for joining me on this explainer. I hope you feel super empowered to tackle those wires and waveforms. Keep learning, keep building, and I will see you next time.